Hello everyone. In this video I want to demonstrate the concept of ordinals. Imagine we have this function y equals x plus 1. When we take this function at the point 0 we get 1. We can then iterate this function again at the point 1 we get 2, and in general when we iterate this function n times starting from 0 we get n, and these iterations grow without a bound. Now let's take a look at this function 1 over 2 minus x. You can iterate this function any number of times, and the resulting values will forever approach 1 and never exceed it. It would make sense to say that the infinitieth iteration of this function starting from 0 is exactly 1. If you try to iterate this function at the point 1, you will get 1 back because it's a fixed point of this function, so you can't do any more, you can't iterate this function further. So let's redefine this function to take the value 1.1 when x equals 1. Now we can still iterate it any number of times. The iterations will forever approach 1, so it would make sense to say that the infinitieth iteration is exactly 1, and we can iterate this function more times after that. When we take the value at the point 1, we get this another point, and then we can iterate starting from that, and we get new values. Now I want to construct a function that has this part here repeated here and here and so on. To do this, I first take a fractional part of x, then I apply the function that I want to repeat, 1 over 2 minus x, and then I add back the integral part of x, and I get this nice repeating function. Now this function you can iterate again as many times as you want and never reach 1, but for approach it you can iterate it infinity times, but you can iterate it any number of times after that and approach 2. You can iterate it infinity more times and get 2, you can iterate it another infinity times and get 3, and so on. We say that this process of iterating this function reaches the value 1 after omega iterations. Omega is the word we use to describe this kind of infinity. We don't usually say omega when talking about the limits in analysis. It's a different concept, although of course it's somewhat related. We need the word omega because in this part of math there are many different infinities. Ordinals are simply the indices of steps in this process and similar processes. So we have the first step, the second step, the third step, and so on. Then the step number omega. So all the natural numbers and omega are ordinals, being the indices of steps in this process. Then we have the next step, we call it omega plus 1. We have the step omega plus 2 and omega plus 3, and then when we do infinity more steps or omega more steps, we get to the step omega times 2. When we do omega more steps, we get to the step omega times 3, and so on. For this function, after iterating it omega times n times, we get to the number n. Now I want to construct a function that you can iterate even more times and still get bounded values. To do this, I want to squish this function so that all this happens inside this unit square where x ranges from 0 to 1 and y also. To do this, I first apply a function that stretches the interval from 0 to 1 into this whole half infinite line where y is bigger than 0. Then I apply the function that I want to squish, our previous function, and then I apply the inverse of that stretching function to squish this whole infinite half line back into the interval from 0 to 1, and I get this function where all these lines that we saw that were of equal size and shape before are now fitted inside this unit square. And then, like I did before, I copy this fragment here and so on, using fractional part of x and all of that stuff. This function we can iterate 1 time, 2 times, 3 times, omega times. When we iterate it omega times, we get to 1/2. When we iterate it omega more times, we get to 2/3. When we iterate it omega more times, we get to 3/4, and so on. Now we can take this process of iterating this function omega times and repeat this process itself omega times, and we'll get 1 as a result. We say that we iterated this function omega squared times, and then we can iterate it omega squared more times, so omega squared times 2 times, and we of course can iterate it like omega more times and 2 more times after that, or another omega squared times. Now when we iterate this function omega squared times n times, we get the value n as a result. Now we can squish and copy this function once more, like we did before, and we get this function. Like before, you can iterate it omega squared times, but now you only get to 1/2, and you can iterate it 5 omega squared times, you only get to like 4/5 or something, or 5/6, I don't remember. And only when you iterate it omega cubed times do you finally get the value 1. And of course you can repeat this squishing and copying as many times as you want, getting functions that you can iterate more and more infinite number of times while still getting bounded values as a result. We could construct a function like this, taking a small part of every function that we defined before. So this one you could iterate omega to the power n for any n. Or if you are familiar with fundamental sequences for ordinals, this is the function that you can define alpha times for alpha being non-ordinal and still get bounded values. These previous functions are maybe more nice in that you could write them as an expression involving only basic arithmetic operations and fractional part and integral part. This is all for this video. Thank you very much for watching.